Hey students, welcome back. Good to see you, or good to have you here. I can't see you, but good to have you here. I'm glad you're watching this video. We're going to learn about thinking like a scientist today and different types of measurement systems and the scientific method today. So something you might have seen before. So I'll kind of skip through this briefly just to kind of give you a review. And as always, my method guy here is always watching me is Beethoven, making sure I'm safe and doing the right thing. So there was the discovery of penicillin in 1928 by Fleming and Forley. And this idea of being able to have an antibiotic that would fight and kill bacteria that had probably several of you, or a version of this if you're allergic to penicillin. A version of this has helped you with an ear infection or strep throat or maybe some sort of a mild infection that you might have had. And what this allows us to do is really launch the field of antibiotics that was done and discovered by accident. This discovery of antibiotics in this particular type of mold that kills bacteria was discovered by accident. So much of what we do in chemistry, called alchemy, was the original work of chemistry, was called alchemy. And alchemy was led by, what we wouldn't call them scientists today, but they laid the groundwork. Alchemists were developing tools and techniques to work with chemicals, mostly to turn metals into gold. So it was a little bit of a greed, or maybe a business strategy, if you want to think of it that way. As their business plan was to turn metal into gold. So they developed all these different techniques and all the different flasks and beakers and even types of burners and heating things up and collecting liquids and collecting gases, all these tubes and stoppers and things that we might see normally in a chemistry class or a chemistry lab. What you associate with a chemist in a lab came out from alchemists. Okay, so alchemists discovered process of separating mixtures and purifying chemicals. They designed an equipment like a mortar and a pestle to take a solid and to smash it down into smaller, finer bits. And things like beakers and flasks and tongs and funnels and even this mortar and pestle here were developed by alchemists. So we still use these to some degree, pretty much as they were a couple hundred years ago. So, but it was a different approach. And so a man named Antoine Lavoisier, a French aristocrat, transformed taking alchemy into more of to the scientific field, the scientific field that is chemistry. He transformed it. He transformed it from a science of observation to a science of measurement. So there's different from seeing something. Then it's important to observe things in science. Hey, if I do this, if I melt this metal, lead, it turns into a liquid, and then I can form it into any shape that I want. If I take a lead and I can solder it and use that to make electrical components, even though that's not what was happening in the day, that's an observation. I can see when I do one thing, it turns into this or it changes into that, versus the science of today is measuring that, adding a number in a unit to that. So that's what Lavoisier started off doing. So he designed a balance that could measure mass to the nearest 0.0005 grams. Very, very accurate and precise. He also showed that oxygen is required for materials to burn. So this idea that oxygen is a part of what we call the fire triangle today. And here's a part of a reconstruction of Lavoisier's laboratory. Unfortunately, Lavoisier was a part of the side of the French Revolution that was killed. He was part of the aristocracy. He was part of a tax collecting taxes for the crown in the French Revolution. So he was beheaded. And so, since he was part of that group, he was beheaded, and many of his experiments and many, many things were not done. Imagine if he would have not been killed as a part of that revolution, and more discoveries would have been made. So much of his equipment was destroyed. Some of it was given back to his widow after the revolution. They kind of realized who they killed. Anyway, that's a little bit of a story into his life there. So what we're going to talk about is a scientific method that kind of came out of some of the methods that Lavoisier used. Okay, and these are the methods. They might differ from time to time, but I want you to understand just the basic steps and how to walk that through. I'm not asking you to memorize these things, but I want you to be able to walk me through in an essay or a description, or tell me in person how you would do a science experiment. So that method is logical. It's systematic approach to the solution of a problem or a question. Okay, problem and question in science are kind of similar to one another, they're synonymous. So logical meaning you thought it through. There's some intentionality behind it. It's systematic means that it's repeatable. It's got a step-by-step process to it. So these steps include making observations, testing hypotheses, and developing theories. So making observations, when you sense or you see some information, so let's say, for instance, the example here is you turn on a flashlight and it does not light. So you made an observation. I had expected when I press the button on this flashlight for it to operate. So it can lead to one question: what's wrong with the flashlight? Why isn't it working? So that's an observation that leads to a hypothesis. So hypothesis is a proposed explanation for that observation. Okay, so you observe, doesn't work. My experience in the past says usually when a flashlight doesn't work, that probably the simplest problem or the most likely problem, most probable problem, is that it is run out of battery. The battery is not working any longer. I need to replace the battery. So I can test my hypothesis by putting in new batteries. And if a flashlight lights, your hypothesis is true. If it doesn't light, your hypothesis is false. And batteries are not the reason for the lack of light. It's something else. Okay, so a false or a quote unquote wrong hypothesis is not failure. You just know what doesn't work. And so if it's not the batteries, it might be something else. It could be something else with the. So you'll do an experiment. An experiment is a procedure that you use to test this hypothesis in experimental design. So when we talk about experimental design, we have to think about variables. One is called the manipulated variable, or what's called the independent variable. And the other is called the responding variable, or the dependent variable, the one that responds. So I change one variable, which is independent, and that change in one variable is going to affect the second variable, the responding variable. So I like thinking as versus independent versus dependent. I think as manipulated, because you think of manipulate, you change and you influence something. Okay, you change it, and because of that change in one, something else is going to respond. Okay, so if you poke your sister in the shoulder, manipulate, poking in the shoulder, the response is probably you probably is going to not going to be a positive response towards you, right? Okay, so this idea of manipulating is changing one variable to then see what the other variable, how the other variable responds to it. So that's called independent and dependent. Okay, so I know you've learned independent and dependent before. Actually, manipulating and responding may help. So this idea of developing theories, hypothesis, if it's repeated over and over again and tested again and again, there's no real number. It's like, 15 times is now a theory. It's not really that tight of a definition, but a theory is a well-tested explanation for a broad set of observations. Notice that it's observation. So a theory will never become a law. We'll talk about a law in a minute, but a theory is a well-tested, best explanation for an observation. Okay, so it can change as new information comes in. So say like the theory, the cell theory, or the theory of evolution, or other types of theories that they are given with lots of information and lots of data and lots of hypotheses and lots of experiments and lots of agreement between different science and scientific groups over the years that said, here is the theory. Okay, and the theory can change as it's updated. So even atomic theory. Okay, we're going to learn a lot about atomic theory, is that there was an understanding of what the atom was in 1860 versus how the atom is now in the 21st century. That theory has changed and updated. It wasn't that they were wrong in 1860s and 1900s and 1910s, right around where a lot of that scientific revolution was taking place, is that was based on the information they had at the time, that was the best theory. So our current theory of the quantum theory of the atom is the best current understanding that is still being practiced and evolving. So again, I said chemistry and science in general is a practice that is changing and evolving. And just because we update a theory doesn't mean that it was wrong, is that we now have more information that scientists have brought to the table. And different, a law is something that doesn't change, and it's not based on observations. It's based on mathematical principles. So the theory of, the gravitational law is based on a scientific and mathematical principle that all objects fall at the same rate. So on the Earth, they fall at 9.8 meters per second per second. They accelerate 9.8 meters per second every second. It doesn't explain the relationship. It just says here is why. Here's the math behind it, and that doesn't change. Laws don't change, theories do. Okay, and a law, primarily in the physical sciences, chemistry and physics, is explaining a mathematical relationship that has been uncovered. So E equals mc squared by Einstein. Okay, F equals ma by Newton. Okay, all these laws of motion and how the universe works are mathematical principles. So those are laws, and new information will not change them because they are what they are. All right, so there's some steps in the scientific method you've seen before. You make an observation. My flashlight's not working. Hey, that flashlight could be that it's out of batteries, or it's an old battery. Maybe someone stole the batteries. I don't know. So you run an experiment, check for batteries, put new batteries in. You run experiments until you see that what was the actual problem. Was it the battery? Was it the fact that maybe the light bulb burned out? Maybe there's not a tight enough electrical connection, that there's not contact with the battery. There might be some other reasons. Someone may have dropped it in water and it's not waterproof. It might be some corrosion on that. So there's experiments to prove or disprove, true or false, the hypothesis. And then based on that, you might do experiments. You might come up with some math related principles that come out of that. And that could be a scientific law, because you've discovered out of your experiments a mathematical principle, like the gas laws, which we'll learn later this year, came from experiments that have a mathematical relationship. So the gas laws that we'll learn later this year are based on experiments but have mathematical relationships. That's why they're called laws. Or if you just continue to see observations, this one chemical reaction seems to react this way in this certain type of environment, there might be a theory, and that is repeated over again. So that's explaining an observation, where a law is explaining the math behind the experiment. And the theories can be improved as more experiments go on and on. Just like a hypothesis can be improved, the theory can be improved as more information comes about. So last thing we'll talk about today is collaboration and communication. Collaboration, communication is important. If we've ever seen that in some of our culture, is miscommunication or the wrong type of collaboration, or people being in the silos and not communicating data back and forth. That's a very important role in scientists. No matter how talented you have a team, one team member can't do it all. She can't do it all by herself. Scientists work together. So many times Nobel Prizes in chemistry and physics and medicine are given to teams of people, or even people that were working independently in different countries, working on different problems, but they came to a similar conclusion about a phenomenon or law or a discovery. So when they collaborate, they increase the likelihood of successful outcome. So they can choose for different reasons. Some do research problems that are so complex that you need different equipment. Some people may have more an understanding of something, more resources, more knowledge, more a broader base. When you broaden your base of understanding, you can solve complex problems. Scientists might do a petroleum chemist is working with an analytical chemist that might be working with a chemist that works for industry that makes clothing, and the three of them together doing research the petroleum chemist could help out the analytical chemist, and analytical chemists can help them out. So these ideas of these different sets of industries, different expertise and equipment. One scientist may have the equipment, the other may have the resource or the people power to use that. So coming together, oftentimes collaboration success is done out of collaboration. So we'll do a lot of that. We'll do that in some limited factor based on some of our distancing this year. But you're likely to work with a team in a lab. You also experience benefits of collaboration. One may be better at there's certain laboratory techniques. Some might be better at recording and phrasing and writing a report together. So a lot of what we'll do this year is writing things, doing work together, even though you may not always be near each other when you do it. You will collaborate together this year. And in communicating, whether you do face by face over a Zoom call like this, or by email or phone, or you go to a conference, or you start a YouTube channel, or you have an Instagram account that is helpful for communicating. There's actually a brand of this on social media today called SciComm, Science Communication, where scientists are trying to communicate science in a way that can be understood not just by other scientists or students, but by the general public. So things like peer-reviewed articles, things that are in journals and even newspapers that are understandable by the audience that it is. So one thing in any communication, understanding the audience you're writing to. So that is our session today on thinking like a scientist. We talked about what it means to think like a scientist, the beginning of it through Lavoisier, the scientific method, and lastly, communication and collaboration. So that's it for this lesson. I hope to see you all soon. Bye-bye.